Chapter 9 is going to become our beginner discussion of polyprotic acids. So to begin, let's look back at some molecules that you know from general chemistry. These two right here, nitric acid and nitrous acid. So which of these two is a stronger acid? I hope you said this one, nitric acid, and nitrous acid is actually weaker. So we're looking at these two. Why is that? Why is this such a stronger acid? Well, if you look at this has 3 oxygens and this has 2 oxygens, and that's the only difference. Well, we know from looking at the periodic table that oxygen is very electronegative. Electronegative means it wants to pull the electrons toward it. So essentially what happens in these molecules, the oxygen is pulling the electrons away from the hydrogen, making it easier for hydrogen to just pop off. Okay? So with hydrogen popping off, that means it's becoming an acid more readily because it's more completely dissociating. So when we're looking at polyprotics, it's all about bond strength and what's going on that makes the acids leaving. So when we look at something like sulfuric acid, for instance, it makes sense that H2SO4 is a strong acid, but its conjugate base, HSO4 negative, is actually a weak acid. Why? These guys are all very electronegative, so it doesn't matter which hydrogen comes off first, but one of them comes off first, because these are all very electronegative, pulling those electrons away from it. By the time that second one is ready to come off, this has a negative net charge, making it much harder for it to leave another electron behind, because leaving another electron behind would make it have a -2 charge, which is going to be harder than just leaving it with a -1 charge. When we're looking at amino acids, these are another perfect example that's going to lead us to understanding bond strength and polyprotics. So with polyprotic acids, you have amino acids, and if you haven't taken biochemistry yet, then you may not be familiar with the way that they work. So amino acids, I gave you guys a table 9-1 in your handout, so look at that with me. This handout shows you all of the different amino acids and these substituents. And so these substituents are these R groups. These are basically, instead of having just, a hydrogen on there or a CH3 group, it can be anything, okay? And so what it is, that anything is shown here, but these don't show you the backbone. The backbone's down here. So every one of these amino acids has the same backbone, and then they have something else coming off of it. So if you look here, each of these also has a pKa. So typically this carboxylic acid, this hydrogen right here can come off, and that has a pKa probably of around 2. Then you've got your ammonium pKa, or your amino group here. So this amino group right here can come off. Okay? Then what we've got going on here, and it should have a little plus up there. So with this hydrogen can come off as well, one of the 3, but it's a little more difficult to come off. So why would that be? It has to do with these pKa's. Remember what we said in class, the larger the Ka, the stronger the acid. The larger the Ka, the smaller the pKa, which means the smaller pKa shown here, this hydrogen should come off first. So what's going on, say when we're doing a titration, is if you start at a low pH and you slowly increase the pH, this hydrogen's going to pop off whenever we get close to its endpoint, and then this one's going to come off at a much later pH. And all that's due to is your bond strength. At what point does it become more favorable for the hydrogen to be in solution than it does to remain attached to the molecule? And all of this is simply based on pH. And so what we're going to learn a lot is first, how do we treat polyprotics? How can we then allow polyprotics to help determine pH? And we're going to do a lot of math to try and figure this stuff out. But before we begin the math, kind of the basic constructs is these equilibrium association constants. Diprotic acids. Diprotic, got 2 hydrogens that can come off. So here, you can write these in a couple different ways. So you can write it as like H2A, okay? Or you can write H2L+. It just depends on what the diprotic form is. Does the diprotic have a charge? Is it neutral? So you just write it like this, but you write it in steps such that the first hydrogen comes off in the first step, the second hydrogen comes off in the second step. So there's a couple ways you can write this, but it all depends on the structure of your actual acid or base that you're looking at. So the rule is that you get a Ka1 for the first hydrogen coming off, and you get a Ka2 for the second hydrogen coming off. Then down here, you can have the exact same thing for a diprotic base. But now you can write it like L. L is for ligand, A is your conjugate base. Whichever form you want to write it at this end. You can write this as A-. Either way is fine. Combine that with water, you're going to produce a hydroxide. So your Kb1 is going to be the first step that produces a hydroxide. And your Kb2 is your second step that produces a hydroxide. Alright, So what I want to think about here, why am I bringing this up? It seems kind of obvious. Ka1, Ka2. Well, we need to be thinking about these in terms of conjugate acid-base pairs. So for instance, Kw equals Ka times Kb. Well, in this case, how do I know which A's and B's go together? Does this A plus this B equal your Kw? Or does this one and this one equal your Kw? Or does this one and this one? You guys see where I'm going with. What are my pairs? Well, look at it and literally see which ones are the inverse of each other. Here you got H2L. Here you have H2L. So these two should go together, which means your Kw for that one would equal Ka1 times Kb2. And the opposite's true. Kw equals Ka2 times Ka1. Oops, Kb1. There we go. Okay. So this is glycine. So this is one of the example amino acids on that worksheet. So if you look at it, it's got the black bone that they all have, and then its R group is the most simple one. So it has just a hydrogen as its R group. So its pKa values I listed here. Now remember, on your exam, so for instance in that table, you're just given the pKa's. So if you need to use the Ka's, remember you got to think about how do you go from P, which means negative log of Ka, to simply Ka. And so make sure you do that math and make sure you can figure out how I got from there to there. Okay? Something else I wanted to tell you. So if this says glycine hydrochloric, okay, or hydrochloride, then this HCl, all that's doing is it's ensuring that the amino acid, my glycine, is in my fully protonated form. And so by adding hydrochloric on the end, all they're saying is this baby is fully protonated. If you were to have something like this, sodium glycinate in particular, then that means it's not fully protonated. So in this example of sodium glycinate, it's got this molecular formula, which means that this hydrogen here on the end, since it comes off first, has been removed and been replaced with the sodium. Okay? So, the things to note with these types of problems, we're going to get into more complicated polyprotics later on, but for this sample, it's going to be a very simplistic, the easiest polyprotic you can have, and this is the kind of polyprotic you're going to be praying you get on the test. Okay? Why is it? So, what I mean by this, notice my Ka here is 10 to the minus 3, and my Ka2 is 10 to the minus 10. Huge difference between them. So this thing is large and this thing is really small. So if I'm asking you to find the pH of this polyprotic, what that means is like almost all of the hydrogen ions are going to come exclusively from the deprotonation here of that first proton, which means this proton coming off doesn't really matter. And so you can essentially pretend that it's a monoprotic. And you basically, if you're given a problem like this one, where you're asked to find the pH of a 0.05 molar solution of glycine, fully protonated, all you have to be concerned about is the first Ka, and you essentially pretend the second one doesn't exist. And so you would work this problem, which is a polyprotic problem, but you work it as a monoprotic. For your homework, that's what I want you to do. Work this problem and figure out what the pH is if you have a 0.05 molar solution of glycine. Treat it like a monoprotic that has that Ka.